This talk has come about following on from his hugely popular 2015 talk on the tales of our forefathers. And in fact, the download viewing statistics alone say why it is so important that you are here today. So thank you very much for taking the time, and it's wonderful that this also will be recorded and kept for posterity as well for today. So thank you very much.
Thank you very much. It's nice to be back. So this talk has 60-minute, 90-minute, and 2-hour versions. It's modular, so I just skip some people. So since this is not the 2-hour version today, I will skip some people. However, as of this morning, the slides are available on my website. So if you want to see what I skipped, you can download the talk from the website. Okay, so this is not a mathematics talk, but it is a talk for mathematicians. It's independent of the talk that I gave here and other places, Tales of Our Forefathers, but I've tried to avoid too much overlap for people who've already heard that. So in particular, I've abbreviated the introduction to make the same introductory caveats that I'm going to do more shortly. I need to move the chair so I can see the screen better. So I'm not a historian. I've no faith at all that what I'm telling you is true. None of the stories was made up, at least by me. I regret this is mainly about forefathers and not foremothers also, but among the 22 mathematicians on the list, there will be one female mathematician. A third caveat is that I'm an analyst, and I learned many of these stories when working on the notes for a series of analysis texts. So I'll be focusing on analysts, but prior to the 20th century, mathematicians were much more universal, and so analysts actually means most mathematicians. Mostly we remember mathematicians by applying their names to theorems and mathematical objects. In this regard, I quote the Arnold principle: if a notion bears a personal name, then this name is not the name of the discoverer. And in Arnold's paper where he quotes this, he also mentions the Berry principle, that the Arnold principle is applicable to itself. The bulk of the first talk was structured around families and events like death. I decided to start this talk with an amusing parlor game, which is a little silly, especially if you take it too seriously. I've also organized the talk around groups of 3, leading to a total of 22 mathematicians. In the modern era, there's enough infrastructure that for the past 50 years, many great mathematicians quickly found important positions and lived rather dull lives, but the lack of many university positions, limited contact between groups, means that this is much less true of the greats 150 to 250 years ago. So the game we're going to play at least 2 rounds of is who are the 3 greatest mathematicians? And I dare say for most mathematicians, the top 3 listed alphabetically are Euler, Gauss, and Riemann, although I must mention that yesterday after tea someone said to me, when I was younger, everybody knew that the 3 greatest mathematicians were Archimedes, Newton, and Gauss, so maybe it's not obvious that these are the first 3. But there are in fact 6 groups of mathematicians when it comes to their choice of orderings among the 3. I wouldn't make a big deal of my personal choice, but you can see it on the side. It's Riemann, Euler, and Gauss. Many put Gauss first, and this really depends on what you give Gauss credit for, which, as I'll explain, is a very complicated issue. So I start with Riemann. He began as a student in Göttingen, but Gauss was not much concerned with students, and so Riemann moved 1847, when he was 21, to Berlin, where he was influenced by Jacobi, Eisenstein, Steiner, and especially Dirichlet. Unintended payback, Dirichlet, as a result of the fact that Riemann was a student there, got credit for work on harmonic functions. We give the names Dirichlet problem, Dirichlet principle, Dirichlet boundary condition, because Riemann learned of them from Dirichlet's lectures and named them after Dirichlet. But in fact, Gauss in somewhat earlier, and Green even earlier, and Thomson preceded Dirichlet, whose work was only published in 1850. Riemann returned to Göttingen in 1849, where he spent the rest of his career, which was another 16 years. Among his students was Dedekind. He always had a sickly constitution, died of complications of pleurisy at age only 39. Two of his students, Hankel, of whose functions you may have heard of, and Roch of the Riemann-Roch theorem, also died at early ages, Hankel at 34 and Roch at 26. What is perhaps most amazing about Riemann is that he has only about a dozen papers, several of them posthumous. There are 6 monumental, multifaceted masterpieces. One single paper begins by defining the Riemann integral, but it's a preliminary to a study of Fourier series. The same paper has the Riemann-Lebesgue lemma and the Riemann local convergence theorem. Another single paper has his basic complex analysis, Cauchy-Riemann equations, removable singularities, Riemann mapping theorem, and the notion of the Riemann surface of functions. This is in one paper. Another paper has all of Riemannian geometry. He started out by defining Riemann metric, used it to describe the notion of a geodesic, and ended by a discussion of Riemann curvature, which generalized from the two-dimensional case, Gaussian curvature. It's all a single paper. There's the celebrated short paper on the Riemann zeta function, which was only 8 pages long, and it included the Riemann hypothesis and his vision of the complex analytic view of the distribution of primes. And there are papers on higher dimensional theta functions and his approach to hypergeometric functions. So that's Riemann. Second on my list is Euler. Euler I discussed in the first talk, so I'll just remind you of some of the salient points and then add one extra story. So Euler was raised in Basel. His father and his maternal grandfather were both pastors, and Euler was expected to follow in the family industry. But fortunately, Bernoulli had been a student at the university with Euler's father, and he was able to convince Euler's father to let Euler become a mathematician. Euler spent his career employed by academies of science, first in St. Petersburg, then Berlin, and when Catherine the Great ascended to the throne, one of the things she knew she wanted to do was get Euler to return from St. Petersburg, and so she got him back. A remarkable thing is that he was totally blind from 1766, but continued to produce many papers until his death. He wrote with the aid of scribes and mathematical assistants. He was remarkably prolific. He had 13 children, but he was prolific in both mathematics and physics. His complete works run to 72 volumes, each in the 400 to 700 page range. It is estimated that 1/3 of all the papers in mathematics and physics written in the 18th century were written by Euler. To show his influence, I want to quote the results of a 1988 poll of the top 10 somethings, we'll talk about that in a second, taken by Math Intelligentsia. Euler had 3 of the top 5. I heard it was top formulae, and that made sense given what I knew. But in fact, it turns out it was people were being asked what they thought were the top 10 theorems, which is kind of crazy since none of the Cauchy integral theorem, the spectral theorem, or the prime number theorem are on the list of these top 10 theorems. No matter, here's the top 10 list in the David Letterman mode, starting with 5 down, so not the top 10, the top 5. And remarkably, all of the top 5 involve mathematicians whose name starts with EU. So the fifth most important is the so-called Basel formula, the sum of the inverse squares, which is Euler. The fact that there are only 5 regular polyhedra, which is usually attributed to Euclid, that there are infinitely many primes, also Euclid. The polyhedron formula relating the number of vertices, faces, and edges, which eventually became the Euler characteristic much later. And the famous e to the I pi plus 1 is 0. Gauss was a young prodigy who came to the attention of the Duke of Brunswick, who in fact supported Gauss first as a student in Braunschweig, later in Göttingen, and finally at Helmstadt, where he submitted his dissertation, which had his first proof of the fundamental theorem of algebra, which, at least in the initial versions, was not something about complex roots, but rather that any polynomial could be factored into a product, of course, real polynomial, could be factored into a product of linear and quadratic terms. Complex numbers came later, and also Gauss discovered that was the way of doing it. In 1801, he published his masterpiece on number theory, and in that year gained great fame for the following work. So the asteroid Ceres was discovered early in that year, but there were only a few observations before it went behind the sun and was no longer visible. With then current techniques, the orbit could not be accurately predicted, and so astronomers did not know where to look for it when it was going to reappear from behind the sun. Using what we now would call the method of least squares, Gauss was able to determine the orbit well enough for the asteroid to predict where the asteroid would be found, and that's indeed what happened. On the basis of this, he got great fame, and fortunately, he got this at just the right time because his patron, the Duke, was killed in the Napoleonic Wars, and because of this work, Gauss was able to get an appointment as the director of the observatory in Göttingen, and in fact spent his entire career as the director of the observatory. Interestingly enough, both Bessel and Mobius spent their careers also as astronomers. His mathematical contributions are staggering. Among the contemporaneously published ones, he turned number theory from a set of ad hoc observations into a systematic field. He developed quadratic reciprocity and the class number problem. He gave the first proofs of the fundamental theorem of algebra. He's responsible for Gauss curvature and the related Gauss-Bonnet theorem. He discovered Gauss's law and did work on harmonic functions. He did important work on hypergeometric functions. He invented what, until high-speed computers came along and other techniques were developed, the standard algorithm for numerically evaluating integrals called Gaussian quadrature, and he developed the least squares and the associated Gaussian distribution. It is widely misunderstood that because he had the Gaussian distribution, he had something to do with the law of large numbers, and that's in fact just not true. Most impressive is the work which was either never published or was published after his death, often in his complete works, including in this unpublished work. In 1811, Gauss wrote a letter to Bessel that included a statement without proof of a version of the Cauchy integral formula. Cauchy only found it 14 years later. So the question is, does Gauss get credit for the Cauchy integral formula?
So when you say found it means the letter or the...
No. So, no, Cauchy found the Cauchy integral formula. So the Cauchy integral formula was published by Cauchy in 1825, and Gauss knew it in at least some preliminary version 14 years earlier. No, I don't believe it. I think the letter was only found many years afterwards. It's something historians probably discovered in the early 20th century or late 19th century. In 1832, so Jonas Bolyai's father had been a student of Gauss, and Gauss wrote to him about his son's discovery of non-Euclidean geometry, saying that Gauss, had actually known of this for 35 years. Gauss discovered what's now called the fast Fourier transform, in fact, even before Fourier's work. It appeared only in his complete works, but it had not appeared earlier. So in some sense, he deserves the credit, but it was essentially forgotten until its rediscovery by Cooley and Tukey in 1965. They discovered the algorithm at exactly the right time because it was just at the point where, using digital computers, you could, in fact, numerically compute Fourier transforms of data important in the real world, and there was an explosion of applications. In fact, Tukey came up with the basic algorithm in the following way. He was a member of President Kennedy's Presidential Scientific Advisory Committee, and the committee had a meeting which they were discussing how they could look at seismic data to try to figure out whether, in fact, there had been Russian nuclear tests and how strong the nuclear explosions were. And overnight, Tukey invented the fast Fourier transform in order to analyze this seismic data. Dick Galwin, who's a famous physicist, was also at that meeting, and he suggested that Tukey get in touch with Cooley, who was an expert on computer programming, to actually program it, and that's where the paper came from. Gauss also discovered the invariant measure for the Gauss map, which takes a number between 0 and 1 into the fractional part of 1 over x. It's a map that, by iterating it, you get the continued fraction expansion of a number, and Gauss wrote about this in a letter to Laplace, stated without proof not only the invariant measure, but the expected connection to asymptotics of continued fraction expansions. He, in essence, intuitively thought that this must be what we would now call an ergodic map. He conjectured the prime number theorem when he was 15, but published nothing on it. He mentioned it in a letter 50 years later. In 1827, Abel and Jacobi revolutionized the theory of elliptic integrals by understanding that the inverse functions were doubly periodic, what we now call elliptic functions. But in his notebooks, starting 31 years earlier, Gauss had this basic idea, at least for a special case of elliptic integrals, namely the so-called lemniscate integral, which is the arc length of a lemniscate. I think I'm going to skip the rest of Gauss. Okay, so we're going to play one more round. Now, I have to warn you that I hesitated going one more round even. I refused to. Yesterday someone was, well, what would I think about so-and-so? Was he number 11? I'm not going, but, I got to pick people to talk about. So if I had to pick the next three, to me they'd be Newton, Hilbert, and Poincaré, and I see my buddy Newton staring at me from the opposite wall. It's the same picture even. He's, of course, not only a great mathematician, but arguably the greatest physicist. In my opinion, his only competition is Einstein, although I guess in Cambridge I should say Maxwell might also be, but to me it's Einstein and Newton. It's not only, of course, mechanics and gravity, but also optics. His greatest mathematical discovery was fluxions, which we now call calculus, but he also was the first person to write down the binomial theorem for fractional powers. He invented repeating divided differences and did the first classification of cubic curves. But to only think of subjects that Newton worked on misses his truly historic contribution to civilization. Before Newton, explanations of nature were mainly magical. Afterwards, the world became just a dynamical system. As Pope put it, nature and nature's laws hid in night. God said, "Let Newton be," and all was light. To which Sir John Squire added many years later, "It could not last, the devil shouted ho, let Einstein be, restored the status quo." And here we see Newton on stamps from a variety of countries. He's no longer, I think, on the £1 bill. Is there even a £1 bill anymore?
No.
And he's still on?
No, just
There's a coin. There's not a bill anymore. I won't focus on the stories about the young Newton when he was home from Cambridge or the priority fight with Leibniz, but I should mention that while we think of him as a great rationalist, he spent almost as much time studying alchemy as physics. And he wrote religious tracts and, in fact, studied Talmud. He was a great director of the mint in his later years. I'm going to skip Hilbert and Poincaré. If there's time, I'll come back to them, but I really want to get to the last trio. So there's a lot on Poincaré in particular. So in the 18th century, the centers of mathematics were clearly France and wherever Euler happened to be. And in the 19th century, I think France and Germany. In the 20th century, we'd have to add the United States and England, and perhaps Russia, all large countries. But if I want to focus on trios, it's natural to ask about small countries. Now, if I had to pick the second most important small country, it wouldn't be clear. We could argue but it's absolutely clear there's no doubt about what the most important, the largest small country is mathematically speaking. It's Hungary. And picking only three mathematicians isn't easy, but if you focus on the first half of the 20th century, to me, they're clearly Ries, Szego, and von Neumann. Of course, there were Ries brothers, so this group of three is 4, and that's how my groups of 3 added up to 22. Remarkably, Ries was a student at the same time as Fayet, but the other 3, namely Emery, Szego, and von Neumann, were all students of Fayet. Friedrich Ries was a Jewish-Hungarian mathematician whose students included Horvath, Rado, Renyi, and Nagy. He did his studies in Zurich and Budapest and then went to Göttingen, where he was very much influenced by Hilbert. In 1911, he was appointed to the University of Kulzavar, but in 1920, at the end of the First World War, there was a treaty in which Transylvania, where this university was ceded to Romania. The town of Kulzavar was renamed to Cluj, And a new university was established in Szeged in Hungary, and the faculty were invited to join the new university. And Ries and Haar founded the Bolyai Institute at the Szeged University. Ries very much wanted a position in Budapest, which was Hungary's greatest university, but there was a firm policy of limiting Jewish professors to one in each department. Feyer was also Jewish and already a professor there, and so during most of his career, Ries was not made a professor in Budapest. In 1945, with the Russian occupation, it's strange to say with the Russian occupation, anti-Semitism diminished, but it's true. As bad as the Russians were, the Hungarians were worse, and Ries was in fact able to move to Budapest, where he spent the last years of his career. He survived the Second World War despite roundups of those of Jewish heritage, going back and forth between Budapest and Szeged. Ries and his brother, as well as Haar, Koenig, and Feyer, never married. Ries told his student Kalmar that he shouldn't marry, but instead should devote his life to science. As one of Ries's students reports, however, Kalmar did get married. This made Ries lose his temper. For a while, he was nervous and impatient to Kalmar. But then he calmed down. Kalmar's wife was also an able mathematician. Ries liked her, as all of us did. Ries could see Kalmar's scientific goals had not been hurt by the marriage.
So he could have well been very jealous.
In 1950, there's a famous 1955 textbook of Ries called Lessons in Functional Analysis, which he wrote with Naj, and it was long a standard text in functional analysis. They wrote it in French because Ries's other primary languages were German, which was not acceptable after the war, and English, which was not acceptable under Soviet occupation. Fortunately, the book was translated very soon after into English and was very popular in its English translation. Ries had been polishing it for many years, as this story from Ray Lorden. So Ray Lorden was an American mathematician, Ray Lorch was an American mathematician who spent most of his career at Columbia, but he was a postdoc in Szeged under Ries, and he told the following story. Ries was a dangerous man with whom to collaborate in writing a paper or a book. He was constantly having new ideas on how to proceed, and the latest brainchild was his favorite. This would lead to disconcerting results for the collaborator, who was perpetually out of step. An example was told me by Rado, Ries's ex-assistant. During the academic year, Ries would lecture on measure theory and functional analysis. Rado would take copious notes. When summer arrived, Ries would depart for a cooler spot. Rado would sweat it out for 3 months, writing up, at Ries's request, all the material to be published in the fall, and to be in publishable form for the fall. At the end of September, Ries would put in his first day at the Institute. Rado would come to the library to greet his superior, proudly carrying 800 pages, which he placed in Ries's lap with great satisfaction. Ries glanced at the bundle, recognized what it was, raised his eye with a mixture of kindness and thankfulness, at the same time a spark of merriment, as if he pulled off a fast one. "Oh, very good, very good. Yes, this is very nice, really nice. But let me tell you, during the summer I had an idea. We will do it another way. You will see when I give the course, you will like it." This took place many years in a row. The book was not written until Ries, probably under the pressure of advancing age, wrote it in collaboration with Naj some 18 years later. Ries was a giant of functional analysis with contributions starting in 1907 for 30 years. Among his contributions are, so I'm going to stop after the first three to say a remark. So first of all, he's responsible for the first formal definition of metric space. So Fréchet is often given credit for this and did indeed define a notion that includes metric spaces, but he required a condition that would essentially let you do something about convergence, but he allowed many possible things for the convergence, and it was Ries that realized the proper condition to choose from the possibilities that Fréchet had mentioned was the triangle inequality. Ries was the first person to make the modern definition of connected set. He was the one who understood that compactness was equivalent to a finite intersection property. And I stop here. So at the beginning of his career, so what I want to emphasize is that while Ries did this sort of highfalutin, fancy functional analysis, at the start of his career, these ideas weren't even known. So he really took the subject from not really even existing to its highest state. He's responsible for finding the dual of Hilbert space, often called the Ries representation theorem. He found the dual of the continuous functions on 0, 1, the so-called which was generalized to the Ries-Markov theorem. He's the Ries of the Ries-Fisher theorem, which in modern books is quoted as the fact that L2 is complete, but they wrote the paper in terms of L2 convergence of Fourier series. He was the first person to write down Holder's inequality for integrals. He defined LP spaces. L stood for Lebesgue, and understood the duality. In fact, as you see, he's responsible for discovering the duals of almost all the classical spaces. About the only one he didn't find was the dual of H1, which made Pfefferman famous. He was the first person to prove weak star compactness of the unit ball in LP. He was the first person to define Hardy spaces. He called them HP after Hardy, and the Ries factorization, which is fundamental, is his. He, independently of Herglotz, found the Herglotz representation theorem. There's a theorem called the Feyer-Ries theorem. There's a theorem he proved with his brother called the F&M Ries theorem. The early work on the spectral theorem by Hilbert was, given Hilbert's background as an algebraist, was done in terms of quadratic forms. The fact that we think in terms of operators rather than quadratic forms is a discovery of Ries. He was the first person to write down the resolution of identity formula spectral theorem. He was the first person to define compact operators. He did the analysis, the spectral analysis that's often called the Ries-Schauder theorem. He invented something called Ries products. He understood orthogonal projection had something to do with minimization. He was the person who invented the notion of subharmonic function and developed fundamental decomposition for subharmonic functions. He is the one who developed the fact that connected components of the spectrum have projections associated with it. He developed the theory of complete vector lattices that are called Ries spaces and their duality. He found a polar decomposition proof of the spectral theorem. He proved something called the Ries-Sunshine lemma, which is connected, a way of proving the Hardy-Littlewood maximal inequality. He proved actually something stronger than the Hardy-Littlewood, the so-called Ries-maximal equality. And he was the one who realized that the Hardy-Littlewood maximal inequality implied the Lebesgue differentiation theorem. So this work was done in his 50s. He also did had the first rearrangement inequality for convolutions. It appeared in a paper that Hardy wrote or published. So there are a number of papers that Hardy published where he said, my friend so-and-so sent me a letter that I thought was so important it should be published. And he went ahead and published it in the proceedings of the LMS. So the Ries convolution theorem appeared in a paper of Hardy, but in which he said it was Ries's work. Okay, so that's F. Ries. Not surprisingly, given that F. Ries was a Jewish-Hungarian mathematician. His brother Marcel was also a Jewish-Hungarian mathematician. His students included Kremer, Hiller, Frostman, Torin, Gording, and Hormander. He was Frederick's younger brother and did his studies in Budapest under Feyer. The year after getting his PhD, he was invited to visit Sweden by Mittag Leffler, spent the rest of his career in Sweden, initially in Stockholm, and in 1926 he moved to Lund, where he stayed until his retirement in 1952. Undoubtedly, his most famous result was LP boundedness of the Hilbert transform. He proved this theorem in 1928 in order to show LP convergence of Fourier series. He proved the result initially for even integers, and then proved a special case of what's now called the Ries-Torin theorem on interpolation. It was his student Torin that proved his full conjecture, but the special case he needed, he was able to prove and use that to complete the proof of the LP boundedness. Interestingly enough, earlier than his work, Kolmogorov had proven that the Hilbert transform of an L1 function is weak L1, and with modern technology, it's very easy to get the Ries result out of Kolmogorov's result. Besides this result, he wrote the definitive book on Dirichlet series with Hardy. Again, an interesting story. So the book was published in 1917 by Ries and Hardy, and in the preface, Hardy writes, Ries and I, in 1914, sat down and sketched out the contents of a book we intended to write on Dirichlet series. Unfortunately, I have been separated from direct contact with Ries by the war. So I finished this book. I hope he doesn't mind my adding his name to the... he also defined Ries means, and he was the first. He proved Hahn-Banach type theorems for positive functionals, and in fact did this before Hahn and Banach. He used this to do the solvability of the Hamburger moment problem, and he's the Ries of the Ries-Torin theorem. He found the Ries criteria for compactness of subsets in LP, and he's also, of course, part of the theorem with his brother, the F&M Ries theorem. Like his brother, he was a lifelong bachelor, but I was told the following story by an attendee at an orthogonal polynomial conference in Budapest. One evening, a group went out to a cafe and were chatting about math. A young woman approached them and said, "Excuse me, but we're from Sweden, decided you must be mathematicians. Our grandfather was from Hungary. He was also a mathematician. We wonder if you heard of him. His name was Marcel Ries." Zago was also a Hungarian Jewish mathematician. In 1913, when he was an undergraduate, his friend Polya, who was then a postdoc of Berlin, returned to Budapest for the holidays and told Zago his conjecture about the asymptotics of tuplets determinants, which at the time were all the rage. And shortly thereafter, in 1914, when Zago was 19, he proved what's often called Zago's theorem, a subject which he and others, including me, have often returned to. When the paper was published the next year, Zago was serving in the front as a lieutenant in the Austrian army. Remarkably, he found the second term in this asymptotics, sometimes called the Strong-Zago theorem, in 1953, 39 years after he found the first term. After agreeing in Budapest and then a postdoc in Berlin, he was appointed a professor in Königsberg in 1926. But after the rise of the Nazis, he fled to the U.S., first to Washington University in St. Louis in 1936, and then he was appointed chair of the Stanford Math Department in 1938. He turned what was essentially a provincial department into a world-class one. He was the founder of the theory of orthogonal polynomials on the unit circle and a great expert on classical orthogonal polynomials. He was one of the great classical analysts of the 20th century. This is not the greatest picture, but I couldn't resist using it. This is a picture of Zago on the left and Polya on the right, taken just after they'd signed contracts with Springer. There's a famous set of problems and analysis by Polya and Zago, and this was a picture taken of them just after they'd signed the contract. About 10 years ago, I gave a talk at NYU about Lovener's theorem on monotone matrix functions and expressed some sadness that Lovener was never elected a member of the U.S. National Academy of Sciences. Peter Lax was in the audience and said, you know, neither was Zago. I was incredulous, but that evening I could check on the National Academy website and confirm that in fact Zago was never a member of the Academy. So I asked Lax about it the next day. I said, this is crazy. And here's what he said to me. You know, in those days the Academy was an old boys club. I'm not sure there was anyone in math from Stanford until Paul Cohen was elected after he got the Fields Medal, and Paul tried to fix that. One day I got a call. Peter, this is Saunders. Who is this Polya? Polya was in fact elected, but by then Zago had Parkinson's, and that was considered disqualifying. And you know, I think Zago was the deeper mathematician. That's what Lax said, and I actually agree with it. Von Neumann. So von Neumann was born Janos Neumann with no von in Budapest. His father was a wealthy Jewish banker and purchased a Hungarian title, which when Janos was 10, and not the father, but Janos decided that he should add the royal, when he went to Germany, he would add the royal von. He became Johann when he worked in Germany, and after coming to the United States, he started using the name John and was universally called Johnny. Johnny was a child prodigy, and his father arranged tutoring. The stories say both Zago and Fekete tutored him and were both very impressed. He was the ultimate double major. He registered as a math student at Budapest and at the same time studied chemistry, first in Berlin and later in Zurich, returning to Budapest only to take his exams so that he could get a math degree. And he didn't hesitate to discuss math, for example, with Weil in Zurich, even though he was officially a chemistry student. In 1926, when he was 24, he got in the same year, an ordinary diploma in chemistry from the ETH and a PhD from Budapest for revolutionary work in set theory, including formulating the now standard definition of infinite ordinal numbers. He then moved to be a Privatdozent in Berlin, and then was in Hamburg, and spent a year during that period in Göttingen studying with Hilbert. He went to Göttingen because Hilbert was an expert in mathematical logic, which was his specialty. I'll come back to that a little later. In 1930, von Neumann was uneasy both with the unlimited job market in Germany and the unstable situation. He went to the U.S. initially as a visitor and then professor at Princeton. And from 1933 until his death, he was a professor at the Institute for Advanced Study. He died of cancer at the age of only 53. Some think might have been caused by his war work on the atomic bomb project, where he was, in fact, exposed to some amount of radiation. To fans of unbounded operators, von Neumann's great 1927 paper stands out. It had all the basics for the first time, the notion of closed operator and closure of an operator, and of self-adjointness, the proper definition of unbounded self-adjointness, of deficiency indices, the spectral theory and the theory of self-adjoint extensions, with its consequences for positive operators, and also operators commuting with a complex conjugate. During this 1927-1930 period, von Neumann developed this theory and its applications to quantum mechanics, which included his work also on quantum measurement theory and quantum statistical mechanics. This is an impressive opus for a life's work, let alone for a 3-year period. But the remarkable thing is that during this 3-year period, he was doing lots of other mathematics. It includes his joint work with Wigner on eigenvalue crossing embedded bound states, the continuation of his earlier work on the foundations of mathematics on set theory, his founding of the subject of game theory and the first work on the existence of equilibria in economics, and his discovery that the Banach-Tarski paradox is connected to the non-amenability of the rotation group in 3 or more dimensions. I mentioned this work with Wigner on embedded bound states. It's a relatively minor work on von Neumann's, but it's actually a very, it's a subject that, it's a little industry in the theory of Schrödinger operators, so I have a little personal story. So one of the things I discovered, this was an example where you actually have a bound state embedded in the continuous spectrum, which is an unusual phenomena. And one of the first things Kato became famous for was finding non-existence, that under certain conditions on the potential you didn't have any, and it turned out if you looked at the Wigner von Neumann paper, their example was a counterexample to Kato's theorem. And the reason it was a counterexample is that they gave a way of constructing their example, and then they did the arithmetic wrong. They didn't put all the details in, but you could figure out what they did. In the middle of the paper, they used the fact that cosine x over sine x is tan x. And when they did this, there's a remarkable cancellation, and the actual potential they wrote down, which was wrong, was okay. I, who at the time was a graduate student at Princeton, Wigner was just before Wigner retired. I went to see him about something else, but I said, you know, there's this mistake in your paper. He looked at me and thought for a second. You know, Johnny did that calculation. Besides this array of work in the 1920s, von Neumann founded the theory of operator algebras, the initiator of modern ergodic theory, and he did important work on harm measure. He co-authored a basic book on mathematical economics, did the foundational work on lattice theory, and was a founder, arguably the founder of modern computer science. The standard architecture of digital computers is named after him. He did numerical analysis, hydrodynamics, and work on cellular autonoma. He was a key figure in the development of nuclear energy, initially as an important leader in the Manhattan Project. It was his calculations that led to the decision to detonate the atomic bombs dropped on Japan at high altitude to cause maximal damage. After the war, he did joint work with Teller and Ulam that led to the nuclear physics behind the H-bomb. Peter Lax pointed out that if there were Nobel Prizes in the relevant area, and if von Neumann had lived long enough, he would have likely been a winner of 4 in mathematics, where of course there isn't a Nobel Prize, in physics, where I think Peter's being naive if he thinks von Neumann would have ever gotten a Nobel Prize, computer science, where there isn't a Nobel Prize, and economics, where at the time there wasn't. However, von Neumann founded the idea of using game theory, and there are at least 3 different Nobel Prizes, not winners, but 3 different prizes, some of them to multiple people, for applications of game theory to economics. I want to end my discussion, and I think I have time, it's a good story, by some fascinating history behind the von Neumann and Birkhoff ergodic theorems. In early 1931, Bernard Koopman, who was 31 at the time, published a short note that explained that measure-preserving dynamics induced unitary operators on L2 and suggested the newly discovered spectral resolution of Stone and von Neumann might be significant, but he didn't do anything further with this idea. That said, by realizing that operator theory could be used to study the issue of the ergodic hypothesis, Koopman was certainly the godfather of ergodic theorems. The year before, when Koopman realized this, he did tell von Neumann, who within a few months found what is called the von Neumann or mean ergodic theorem. Von Neumann's proof relied on the spectral theorem. Von Neumann mentioned his result to E. Hopf, who found the proof you now find in most books. If one knows the spectral theorem, von Neumann's proof is simple and elegant, but the spectral theorem was regarded until the 50s as a hard, mysterious theorem, and Hopf's proof was regarded as more accessible and simpler. At the beginning of October 31, von Neumann, then in Princeton, went to New York, where Koopman was on the Columbia faculty, told Koopman of his result, wanted to confirm that Koopman hadn't found it independently, because he wanted to be sure to give Koopman credit if he had. Koopman was enthusiastic and suggested von Neumann publish his result in the Proceedings of the National Academy of Sciences, which is where Koopman's note appeared. At the meeting of the American Math Society in New York, von Neumann told Stone and Hopf of his result, and that's when Hopf found his proof. And von Neumann requested that Hopf submit his paper to the Proceedings of the National Academy, and requested that Hopf explicitly ask that his paper only appear after von Neumann's. Still later in that same month, Koopman and George David Birkhoff, who was considerably older, came to Princeton for the opening of the old Fine Hall, and there Koopman and von Neumann told Birkhoff of von Neumann's result, knowing of Birkhoff's long interest in the quasi-ergodic hypothesis. Within 6 weeks, Birkhoff had found the special case of what's now called the Birkhoff or individual ergodic theorem, at least in cases where the flow came from analytic differential equations on a compact manifold. This, too, he published in the Proceedings of the National Academy of Sciences. This brings us to the priority fight, or perhaps, since it was mild as these things go, I should say priority spat. Still, the feelings engendered at the time in 1928 were intense enough that 35 years later, when I was a graduate student at Princeton, I heard the story. The issue is that while Birkhoff was clearly motivated by von Neumann, who was certainly first, Birkhoff was more senior, a member of the National Academy, and most importantly, a good friend of the managing editor of the Proceedings of the National Academy, the famous Harvard chemist E. Bright Wilson. Wilson arranged for Birkhoff's paper to jump the queue and appear in the 1931 volume rather than in the 1932 volume, and so it had in it an earlier communication date than von Neumann's paper. While Birkhoff did mention von Neumann, the implication that von Neumann's work was at best independent and possibly later. Now, for background, you have to realize that at the time Birkhoff was a senior professor, then 47 years old. Koopman and Stone had both been his students. Hopf was his postdoc at the time. He later moved to MIT, where he worked with Wiener. He's the Hopf of Wiener-Hopf. Von Neumann was younger. He was 28 when he found this theorem. And like Hopf, Koopman, and Stone, only a 1926 PhD. Moreover, he was foreign and Jewish, but he was hardly a powerless postdoc. He was recognized as a Wunderkind and was a protege of Oswald Veblen, who had attracted von Neumann to Princeton as a professor only 2 years out of his PhD. Veblen was shortly afterwards the founding head of the math department at the Institute, and von Neumann was one of his first appointments there. If anyone was more established in American mathematics than Birkhoff, it was Veblen. He and Birkhoff were both students of Moore, but Veblen was slightly older. He was a postdoc when Birkhoff was a graduate student. A historian who studied this case conjectures that Robertson had asked von Neumann to write a letter so that Robertson could in turn show it to Veblen. In any event, Veblen intervened, perhaps using Koopman and Stone, and got Birkhoff to agree to write a paper with Koopman in the proceedings, which had nothing in it but a description of the history and clearly stated von Neumann's priority. So the story had a happy ending. If I have time, I'll come back. So there are three personal heroes. I'll at least show you their pictures. Kato, in fact, this is the year of the 100th anniversary of his birth. There was a lovely conference in Tokyo in honor of that. But I'm going to skip this. Loevner is a personal hero. I will skip this. Well, maybe I'll at least quote one. So I want to conclude Loevner. So Lippmann Bayes was Loevner's student, and he in I believe it was the memorial issue after Loevner died, he wrote the following, which I think is just lovely. Loevner was a man whom everyone liked, perhaps because he was a man at peace with himself. He conducted a lifelong passionate love affair with mathematics, but was neither competitive nor jealous nor vain. And I ask you to think how many first-class mathematicians you can think of who are neither competitive nor jealous nor vain. His kindness and generosity in scientific matters to students and colleagues alike were proverbial. He seemed to be incapable of malice. His manners were mild and even dissident, but they hid a will of steel. Without being religious, he felt strongly his Jewish identity. Without forgetting his native Czech, he spoke pure and precise German. Without having any illusions about Soviet Russia, he was a man of the left. He was a good storyteller with a sense of humor which was at once Jewish and humanistic. But first and foremost, he was a mathematician. Jablonski I will also skip. Okay. Nazi mayhem. The history of 20th century mathematics, you can't avoid facing the horror of the impact of the Nazi and communist systems. With death camps, the Nazis were much worse, but only by, the Soviet system looks measured only because you compare it with the Nazis. The persecution of the Soviet system of various mathematicians was awful. Since many Central European mathematicians were Jewish, the impact of Nazi behavior on mathematics was noticeable. I start by mentioning three mathematicians who were murdered in the death camps, all in Theresienstadt, where the Germans tended to send intellectuals. Blumenthal, who was murdered at age 68 in 1944. Pick, who was murdered at age 82 in 1942. And Alfred Tauber, who was murdered at 75 in 1942. There's another trio I won't honor by including in the official list, but I should mention them in this context. That's Bieberbach, Blaschke, and Teichmuller, truly evil men. Teichmuller was the most virulent. He was an SS member from 1931 when he was 18, and he led student protests against Jewish professors. He prevented Landau from lecturing on Jewish mathematics. He felt it was only appropriate to discuss Aryan mathematics. By the direct order of Hitler, he joined the army and he was killed on the Eastern Front. The irony is he might have been forgotten mathematically if it wasn't Lippmann Bayes had decided to name many things after him. So Teichmuller spaces, Teichmuller principle, Those are all from a paper of Bayes. If Bayes had never written that paper, we probably would not know of him as a mathematician. Bayes was a Latvian by birth and a student of Lovner and barely escaped the Nazis. He happened to move from Prague to Paris just after the Munich Agreement and before the Germans marched into Czechoslovakia, and he moved to Marseille just 10 days before the fall of Paris. And there he managed to get a visa to the U.S., later became a professor at Columbia, president of the AMS, and was a chair of the math section of the National Academy of Sciences. Bieberbach was for long a major power in German mathematics. He was, for example, the long-time editor of the Mathematician. He wrote often about racialist theories and actively persecuted Jewish mathematicians, pressuring them to resign from Jewish honorary societies. Blaschke was the least bad of the three, but there's one story that convinces me he must have been pretty bad. Zago has had a reputation of being soft-spoken and gentle. He used to regularly teach the complex analysis course at Stanford. One day a student came to him and said, "Professor Zago, how come what all the other professors call Blaschke products, you just call products?" Zago replied, "I will not say that man's name." I was going to skip Blumenthal, who was actually Hilbert's first student. Pick was Viennese, born in Vienna, but got his PhD from Vienna, but he spent most of his career at the Charles University in Prague, which was a German-speaking university. There he served as dean, and one of the things he was responsible for is he gave Einstein his first professorship in 1910. He retired in 1927, returned to Vienna, but fled from there at the time of the Anschluss. But he fled to Prague, and after the German invasion, he was arrested and sent to Theresienstadt eventually. He's, of course, known for the Pick interpolation problem, and Pick functions, Pick theorem, Pick matrix, Pick interpolation are all due to him. Tauber was born in Bratislava, but spent most of his adult life in Vienna. He couldn't find an academic position. He worked from 1892 till 1908 in an insurance company, and the rest of his career as professor of actuarial science. He's best known for a result which he proved in 1897, which is the Tauberian theorem. I'm not going to discuss it in detail, except that starting 15 years later, Hardy and Littlewood proved numerous theorems which they thought were analogous to Tauber's theorem, and so they called them Tauberian theorems. In his great 1932 paper on the Wiener-Tauberian theorem, Wiener remarked, "I feel it would be far more appropriate to term these theorems Hardy-Littlewood theorems, were it not that usage has sanctioned the other appellation." I may return to Landau, Koenig, and Marcinkiewicz, but I want to get to the final three. So we'll see who I return to at the end. My final trio is a bonus selection. I start with a bonus personal hero, namely Mark Krein. So Mark Krein was a Jewish Ukrainian mathematician who was born in Kiev in 1924 because his father did not want him to study mathematics. He ran away to the University of Odessa, and except for a brief period of evacuation during the Second World War, he spent the rest of his life in Odessa, which is a town on the Black Sea. His students include Brzezinski, Glasman, Kochberg, Millman, Naimark, Rutman, and Soknovich. He got his degree in 1929, and in the 30s he ran a world-class center of functional analysis out of the University of Odessa, collaborating often with his friend Akiezer, who was based in Kharkiv. After the war, he suffered terribly from official Ukrainian anti-Semitism. He was accused of having Zionist tendencies on the basis of having so many Jewish students in the 1930s. He was dismissed from his university posts and spent the rest of his career in lower status institutions. He was forbidden to have Jewish students, so that Kochberg, who regarded himself as Krein's student, wasn't officially his student. He still drew good students and collaborators and ran a lively seminar. He worked on a wide array of specialties, and in each of them wrote seminal papers. He was not allowed to accept any invitations outside the Soviet Union, and it was difficult for foreigners to see him. One of the few exceptions was he attended the 1966 Moscow ICM, where he was a speaker. In 1939, he was made a corresponding member of the Ukrainian Academy of Sciences, but never a full member. He won the Wolf Prize in 1982, but he wasn't allowed to attend the prize ceremony, and in 1979, he was made a foreign member of the U.S. Academy of Sciences. I end my discussion of Krein with two funny stories. Kochberg was a co-author of Krein on several books, including a wonderful book on trace ideals. Like Ries, Krein kept wanting to expand and change the scope. Kochberg explained the following true story became something of a joke in Krein's circle. One day, Kochberg met Soknovich, another of Krein's students, who asked him, "How's the book going?" "Well, it's 85% ready," Kochberg replied. "Then why do you look so sad? That's wonderful." "Yes," Kochberg answered, "but if you'd asked me yesterday, I would have said it was 95% ready." In 1981, I visited Moscow and Leningrad, and I was told the following joke in both places. So it was making the rounds among Soviet mathematicians at the time. A delegation from the American Academy of Sciences makes an official visit to the Ukrainian Academy of Sciences. Towards the end of their visit, the Academy president approaches the American head and asks him, "We wonder, what do you think of our academy?" "Oh, we've talked about that and decided the Ukrainian Academy must be the best academy in the world." Relieved, the president smiled. "I'm so glad to hear that, but why did you reach that conclusion?" "We decided any academy where Mark Krein is only a corresponding member must be the greatest academy in the world." There's a postscript to this story that shows the danger of telephone. When I returned from the Soviet Union in 1981, I often told other people this joke. I know I told it to Peter Lax. I think I didn't tell it to Louis Nierenberg. About 25 years later, I sat at the same table as Louis at a banquet in honor of Shmuel Agmon's 85th birthday conference, and Nierenberg said to me, "You know, my favorite Barry Simon story is the time you told the Ukrainian Academy such and such." Now, I always wondered, I was suspicious that it was Peter. So recently, a wonderful biography of Peter Lax appeared, written by one of Lax's students, Reuben Hirsch. And there's a chapter in it called Peter Stories. And in the middle of the chapter, there's a paragraph that says, "A certain American mathematician," he says a little bit about who Mark Krein is, and then he says, "A certain American mathematician visited the Ukraine and told the Ukrainian Academy such and such." Okay. So I wrote to Hirsch. I said, "Who is that famous American mathematician?" He said, "Oh, it's you. But Louis Nierenberg said you said it didn't happen to you." Now, I had never been in the Ukraine till this summer, but I told the story, and somehow in the retelling, it eventually became. Emmy Noether was a German Jewish mathematician. Her great-grandfather was Elias Samuel, was forced to change his name by Napoleonic edict, and he changed it from Hertz Samuel to Hermann Noether mit an umlaut, and later her father Max decided to change the spelling to O-E. Her father was also a mathematician, was in the school of Albert Clebsch and Paul Gordon. Gordon will play a role shortly. They're, of course, mainly known for the Clebsch-Gordon coefficients. Gordon's approach was very computational. Here's what Weil wrote of him. There exist papers of his with 20 pages of formulae are not interrupted by a single word of text. It is told that in all his papers he himself wrote the formulas, only the text being added by his friends. When Hilbert solved a major problem in invariant theory with an existence proof rather than an explicit construction, Gordon announced, "This is not mathematics, but theology." When Emmy was 18, she obtained a certificate that would have allowed her to teach French and English, and it was assumed she'd become a school teacher, but she decided to pursue university studies. She was one of 2 women among almost 1,000 students at the University of Erlangen. She lived in the town of Erlangen, and her father was a mathematics professor at the university. She was not able to get official course credit for the courses she attended unless she got the explicit permission of the professor to take the examinations. After about 2 years, her interest shifted to mathematics, perhaps because her younger brother Fritz had started doing mathematics. He's the one who later discovered the index of integral operators. In 1903, she spent a semester in Göttingen listening to lectures of Blumenthal, Hilbert, Krein, and Minkowski. She spent only a semester there because it became possible for women to enroll officially in Erlangen. In 1907, she submitted a thesis to Erlangen entitled "On Complete System of Invariants for Ternary Biquadratic Forms," which was written under the direction of Gordon and had 300 and some odd different forms that fourth degree polynomials in 3 variables had a set of invariants that led to this number of possible natural forms. It was very much in the Gordon it's 331. It was very much in the Gordon calculational invariant mold, ended with a table listing explicitly 331 covariant variants for ternary quartic forms. In his memorial address, Weil speculated about the horror Gordon would have felt at the later embrace of abstraction by his student. She continued to write papers in Erlangen with no official connection in the university till 1916, when she was invited to Göttingen. Klein, and especially Hilbert, had become interested in the general theory of relativity, and they thought her expertise in invariant theory could be useful. Initially, she received neither appointment nor salary, and Hilbert's attempt to get her appointed Privatdozent failed, but included a famous exchange during a meeting of the faculty senate on the issue. His opponents argued, how can it be allowed that a woman become a Privatdozent? Having become a Privatdozent, she could then become a professor and a member of the university senate. Is it permitted a woman enter the Senate? What will our soldiers think when they return to the university and find they're expected to learn at the feet of a woman? To which Hilbert replied, I do not see the sex of a candidate as an argument against her admission at Privatdozent. After all, the Senate is not a bathhouse. Initially, Noether was a lecturer in a course that was officially taught by Hilbert. But within a few years, Hilbert did in fact get her appointed a Privatdozent and obtained a small stipend for her. Her first great result is in mathematical physics and is unknown to many mathematicians, although rightly celebrated among physicists. What is called Noether's theorem among physicists asserts the equivalent of conserved quantities and continuous symmetries. For classical systems with finitely many degrees of freedom, this is an almost trivial consequence of Poisson brackets and Hamiltonian flows, but Noether in fact discussed it from a Lagrangian least action point of view, and also that allowed her to discuss it in a field theory context. But even the finite degree classical case, her result was new and very interesting. For example, she was the first who understood conservation of angular momentum was connected with rotational invariance of the laws of motion. Einstein wrote in a letter to Hilbert, "Yesterday I received a very interesting paper on invariance from Miss Noether. I'm impressed these things can be seen in such a general way. It would do the old Göttingen no harm to be sent back to school under Miss Noether. She certainly knows what she is doing." It must be emphasized this idea has been a touchstone of modern theoretical physics. Once quantum mechanics were discovered and Poisson brackets were replaced by commutators, the theorem shone even more brightly, and symmetry became a basic building block of new discoveries in particle physics. As one physicist put it, Noether's theorem to me is as important a theorem in our understanding of the world as the Pythagorean theorem. I'm not alone in having been profoundly influenced by this theorem. As a freshman at Harvard, I read about this result in the mechanics book of Landau and Lifshitz, who didn't mention Noether's name. It was the first time I saw breathtaking beauty in mathematical physics, and I told all my friends about it with great excitement. I'm embarrassed to say that once I learned it was called Noether's theorem, I assumed it must be due to her father, Max, who I knew was some kind of physical scientist, because I couldn't imagine a connection to the abstract person whose name appeared in my algebra classes under Noetherian rings and chain sequences and stuff like that. This brings me to the period of her contribution to algebra, which makes her one of the greatest mathematicians of the 20th century. Together with Brouwer and Artin, two younger mathematicians greatly affected by her, she pioneered the idea of algebra as abstractly defined structures. This idea is so central, one forgets it wasn't always there. She had great influence on many younger mathematicians who were called Noether's boys, among them Alexandrov and van der Waerden. Here is what Weil had to say in her memorial. "When I was called permanently to Göttingen in 1930, I earnestly tried to obtain a better position for her, because I was ashamed to occupy such a preferred position beside her, whom I knew to be my superior as a mathematician in many respects. I did not succeed. Tradition, prejudice, external considerations weighed in the balance against her scientific merits and scientific greatness, by that time denied by no one. In my Göttingen years, she was without a doubt the strongest center of mathematical activity in Göttingen, considering both the fertility of her scientific research program and her influence upon a large circle of pupils. Besides her championing of abstraction, she had contributions to ideal theory and non-commutative algebra, and she made very important contributions to algebraic topology. As Hilton tells the story in his brief subjective history of homology, Emmy Noether recognized that what Alexandrov and Hopf were talking about and what Lefschetz had talked about should not be thought of as numbers, but as abelian groups. So really one should credit Emmy Noether not with the discovery of these topological invariants, but with the understanding of their mathematical place. She recognized the homology groups and that the Betti numbers and torsion coefficients were merely numerical invariants of isomorphism classes of finitely generated abelian groups. She always lived on a meager stipend. I think I'm going to skip. She died of a botched surgery. And I'm going to skip this, but I will end Noether because I want to get to my last person. I can't resist ending my discussion of Emmy Noether with one image I found on the internet. So the last of the mathematicians is a Scottish mathematician named William Thomson. He was the son of a math professor at the University of Glasgow. He was a bit of a prodigy. He had published his first papers while an undergraduate at Cambridge at age 17. In 1846, the chair of natural philosophy at Glasgow opened up, and Thomson's father used his influence to get his 22-year-old son appointed to this position, to this professorship, a position he occupied for over 50 years. He has two notable mathematical contributions. One is that together with Gauss and Green, he was a key participant in understanding higher dimensional analogs of the fundamental theorem of calculus. He was impacted by Green's work and found what is now usually called Stokes' theorem. So why does it have Stokes' name if it was due to Green and Gauss and Thomson? In a postscript to a letter that Thomson wrote to an academic friend at Cambridge, Stokes, he mentioned the theorem, but neither gave a proof of it nor mentioned Green's related work. In February 1854, Stokes made the proof of the theorem a Smith's Prize examination question at Cambridge on a test taken by the youthful James Clerk Maxwell. Maxwell later developed the mathematical theory of electromagnetics, and in his 1873 masterpiece, in a footnote to Article 24, he attributes the theorem to Stokes, whose name has appeared on it ever since. Thomson's other great mathematical contribution involves the basics of potential theory and harmonic functions. In 1867, he and Tate, in their treatise on natural philosophy, introduced the name spherical harmonic because the two-dimensional analogs were cosine and sine, and those are standard harmonic functions in the sense of music. And so they called these things, these were musical harmonics. They called the corresponding functions on the sphere spherical harmonics. In the end, this name spherical harmonics not only stuck, but came to the general term harmonic function. Thomson published over 600 papers, was elected to the Royal Society when he was 27, and served as its president from 1890 to 1895. Of course, naming harmonic functions is kind of neat, and he sounds like he had impressive credentials, but you may be puzzled why I picked as my final choice someone I suspect many of you, now some of you do know the punchline, have probably never heard of, and doesn't seem like he's in the league with the other 21. I'll add to the mystery by saying, by the end of the 19th century, he was widely regarded as Britain's greatest scientist since Isaac Newton. For Thomson made important contributions to physics, especially to the foundations of thermodynamics. Moreover, he was a key figure in the first successful transatlantic telegraph cable, which used some of his designs for its hardware. For this, he was knighted in 1866 and made a baron in 1892. He took his baronial name after the river that traversed the University of Glasgow campus, the Kelvin. In fact, Thomson is Lord Kelvin, and that's why he's on the list. One of his biographers said that during the first half of his career he seemed incapable of being wrong, while in the second half he seemed incapable of being right. In 1896 he wrote to Fitzgerald, "Symmetrical equations are good in their place, but vector is a useless survival, an offshoot from quaternions, and has never been of the slightest use to any creature." He pushed widely incorrect estimates of the age of the Earth and the Sun. He opposed Darwin's theory. He fought Rutherford's theory of radioactivity, saying it was an unphysical phenomena. He was, however, probably never said the quote widely attributed to him just at the end of the 19th century, that there's nothing new to be discovered in physics now. Our future discoveries must be looked for in the 6th place of decimals. I hope you've learned that our forefathers are fascinating people and that you'll consider using Mr. Google and Miss Wikipedia to look up names you find on theorems. And finally, a word from our sponsor. So I have the AMS now 2 years ago published a 5-volume set of books. I take every chance to do marketing that I can, particularly since with the internet and pirated copies, it's hard to sell books. There are 5 volumes. There's real analysis, basic complex analysis, advanced complex analysis, harmonic analysis, and operative theory. Thank you.
Barry, that was absolutely wonderful and fascinating, and the time just flew by. I'm very glad to hear that Newton got ranked as top physicist, if not in your top 3 mathematicians. And of course, personally, I was really delighted to see Erie Noether featured so strongly in your talk. So that was wonderful. Do we have any questions?
Which of the historic figures would you most like to meet?
Krein. He was alive while I was alive, but I've never met him. I always regret never having had a chance to meet Mark Krein. But of course, that's not right. It even occurred to me that I might read Riemann, so I've never really thought about it. But I really do regret never meeting Krein. And in fact, one of the high points of one of my birthday conferences was someone came up to me and said, "You know, Mark Krein was my thesis advisor, and one day he came in with Reed Simon and said, 'You all should read this.' That made my day." So I would say Mark Krein.
Can I add a PS to that? This is one of my favorite interview questions. Imagine you were told the first time since Newton died, he's been allowed back to Earth, and you had 2 hours with him. What would you do in those 2 hours?
I have no...
You have to have an opinion, otherwise I'm not going to accept you as an undergraduate.
I guess I'm never going to be an undergraduate at Cambridge. But, I don't... We don't speak the same language. I'm not sure I would understand much. The mindset, it's true, he had an enormous impact on changing the mindset, but he still, right? While in some sense nature stopped being magical, to him it wasn't. He was an alchemist. He was a very strange bird.
You never meet strange people?
Of course I do, but I don't know how to talk to them. I meet lots of strange people. I mean, I'm a mathematician after all.
So a national economist in Vienna once told me that Isaac Newton is responsible for the British Empire, namely as master of the mint, he sort of decreed that £1 sterling can be exchanged against £1 of silver anytime somebody brings this, which created a uniform currency in Great Britain, whereas on the continent every small dukedom had its own currency and its own kind of coins, and a lot of value was lost in exchanging one coin against the other. And the other thing he did as master of the mint was he invented these rifflings around the coins so that you could not take some gold or silver from the coins and still have the same value as the coins.
He was also he was.
Could I say, I don't think that's quite right. Some of what you said is correct, some is not. He was made master of the mint at a time when forgers were clipping off bits of silver from the English coin, and the point was that you could make more money by doing that by taking it over to Europe and selling it. So basically, these forgers, if you like, criminals, were devaluing the English currency, and it's said that England might have gone bankrupt but for that. So Newton did play a very important role. He also, I mean, you said he was a nasty character. Any forger he found, he was happy to see him hung. He was
I can believe that.
Not fun at
Again,
all.
I'm not. I don't have anything against Newton. I just don't know how I would relate to.
Do we have any other questions?
One question, all these amazing results of Gauss that were not published during his lifetime, why they were not published?
So that's part of the thing. I discussed that a little in some of the things I skipped. So one thing, he had a famous saying, few but ripe. He also remarked about Dirichlet, that someone had said Dirichlet didn't have many papers, and he said, you don't weigh theorems by a Gross's scale. So it's clear he didn't believe in publishing things that weren't quite ready. That's one factor, but I don't think it's the main factor. There's a totally different theory that may have some partial truth, but so he published this great book in number theory, hoping, and the center of number theory was in fact France, and it was denounced in some ways, not as strongly as historians thought for a while. So there's a famous British historian of science named E. Rouse Ball, who made a very elaborate story about how Gauss got a rejection that, and there may be some truth to that. It's not as true as it was, but anyhow, it's not 100% clear. He had it wasn't publish or perish. He had a position as a director of an observatory. So it isn't 100% clear why he didn't publish. He's not the only one. I believe Hamilton had some important results that he never published, that in my opinion he shouldn't get credit for because he never published it, and he doesn't. In fact, somebody else does, but he did do it first. So I can't explain it, but there were. You have to also realize there were not lots of journals in those days. Contemporaneously with his life, the first major math journal, so-called Creel's journal, was started, but its earliest papers were these papers on elliptic functions by Abel and Jacobi. So the view of publication was different, but it's hard to explain.
We all have kind of different mathematical tastes, I guess. And one of the difficulties with kind of understanding the history of mathematics is that it's easy to think in terms of results, because the results we have now. If I asked you from this group of 22 to pick out the 3 people who you think have the most influence, not in terms of results, but in terms of how we do mathematics these days.
I suspect it would still be Riemann, Euler, and Gauss. It's not, I mean, they all had tremendous influence on, so particularly Riemann's work in complex analysis, it's not merely the results, but the whole way of thinking about the paper that has the Riemann mapping theorem also in some sense gave birth to the modern way of thinking about algebraic geometry.
Sure.
So there's no question, not in terms of results, but in terms of mathematical thought, Riemann's number 1. Gauss maybe would be number 2 rather than Euler, but Euler also, I think it would still be the same 3. It's not just the results. It's they really change the way people think. So I have the same top 3 names.
Can I make a comment which I don't think either of us will know the answer to, but it would be interesting to think about. Oh, I think it's interesting to think about. There's a general statement that people who are successful and famous live longer than the average. So, of course, well, not of course, but it's a fact that Oscar winners live longer than the average film actors. The fellows of a college here that's been looked at carefully live longer than on average, longer than their socio-biological equivalents. And I can give you lots of examples. Well, professors in Cambridge in the 1940s, 50s, 60s lived longer than the people who were just lecturers. Now the question is...
Now, but of course, the lecturers that died early never had a chance to become professors. So you have to rule that out.
Excuse me, that's not true. What happens is that the lecturers retire. Sorry, you have to retire.
Oh, I have to.
They retire at 67, then they die, where the professors live in their 90s. There's a definite, very clear distinction. Now, the question is whether this is true of mathematicians.
So it may very well be, but one of the things that in both talks I mention is there are, of course, famous cases of mathematicians that died very young.
Sure, but that's the question.
But of course that's not. You're asking a much more important question, namely, yeah, sure, there are anecdotal examples, but what's the statistical average? And I don't know, but
what's the mean in the distribution? Yeah.
It also probably is more true in the 20th century than in the earliest centuries, just for the reason that mathematicians, professors' lives are much more comfortable now than there weren't as many professors. Many great mathematicians had lots of trouble before they became professors. It's much more common. I mean, you had Gauss essentially, despite his brilliance, if he hadn't made this, he would have had lots of trouble when the Duke died. Those are things that have changed, and so I suspect the answer could depend on the century, but I don't know. I have no idea.
I mean, he lived pretty long.
Maybe we take this offline then. Any further questions? In which case, I might just invite you, when you leave here, you might want to see some of the art exhibits that we've got around the Institute at the moment. We've got some lovely pieces of art at the moment, so while you're here, you might like to enjoy those. So then now, can I just say thank you so much, Barry. That was just fabulous and enlightening and brilliant. Even for those of us who've seen the first talk, it was just wonderful. We learned so much more this time. So thank you very much for coming back. Much appreciated.